Good morning, everyone, and welcome back to the class of 3205. Can you guys hear me?
Assalamualaikum, sir. Yes, sir.
Yes, yes, sir.
Okay, thank you. So today we are going to talk about resolutions in digital remote sensing or any remote sensing. So before that, we will talk about the differences between image and photograph. And if I recall correctly, then in last class we were having some discussion about image and photograph. I was saying that those are photograph, those are not image, and I'll be discussing that in next lecture. So here you go. In today's lecture, the first topic that we're going to discuss is the image versus photograph. So what's a photograph? A photograph is, for example, back in the day when there was film cameras and people used to say that take a photo of mine, take a photo of mine, right? So whenever you use a film to record the signal of the energy, then you can say that's a photo. Okay, and that's a photograph. On the other hand, image can be recorded using any media, using any technology. Anything, for example, if you scan that photograph, then that one turn into an image. So everything that is stored on our computer, normally we say those are the images. Although, yes, in spoken English, in our verbal communication every day, sometimes we say that, all right, show me that photograph or something, and we indicate towards an image that is stored on our computer. Okay. However, if we really think from this, from the perspective of the definition of photograph and image, then every images, those including the illustrations which are stored on a device digitally, those are images, not photographs. Okay. So there are also one more difference from the perspective of physics. Okay, so the photograph, it can detect from 0.3 micron to 0.9 micron, as I highlighted it here. Okay, so it can detect from 0.3 micron to 0.9 micron. So our here you go. And visible light, that means the light that we see is from 0.4 micron, that's 0.4 micron till 0.7 micron. Okay, so it sees a little bit of UV, that is ultraviolet, and a little bit of near infrared signals. So 0.3 here is the UV. So the photograph, it can record starting from UV and a little bit of near infrared, more specifically, sorry, a little bit of infrared, and more specifically it's near infrared. So near infrared is NIR. Okay, so that's near infrared, near infrared, and that's it. They cannot detect anything more or anything less. However, when we come to the image, that is, for example, whenever you have seen a satellite image, you have never said it's a photograph. Okay. However, whenever you have seen that historical photographs, see, I'm saying historical photographs, which were taken before the sensors were invented, you would be saying aerial photograph. Why? Back in the day, they had these cameras without the digital sensor. They had these films. They took these cameras up in the sky and took the photo using maybe birds or using balloons or maybe some aircraft. So all these images, they are photographed, and that's why we say aerial photograph. But in recent times, when we have drones and we have digital sensor in the cameras, now we say aerial imagery. Okay. Just think about that. Whenever we are talking about these historical photographs taken from the sky, we say aerial photograph, but now we say everything imagery, satellite imagery. So imagery might sound confusing to you because you might not be used to this. We say imagery. Okay, so plural form is imageries. So we say that. Excuse me. So excuse me. So that's the thing. Okay, if you use a film camera, that's a photograph. If you use a digital sensor or anything else, that's image. And images, they can detect even more than this 0.4 micrometers to 0.7 micrometers. They can detect aerosols. And so aerosol is a element that is found in the atmosphere. So they can detect aerosols. They can detect ultraviolet rays. They can detect near infrared. They can detect middle infrared. They can detect thermal infrareds. So the range of signals that an image can detect, which is retrieved from a digital sensor, ranges from ultraviolet to the thermal infrared. And sometimes they could detect with the fine details of these signals. For example, hyperspectral imagery. So in hyperspectral imagery, the bandwidth is 0.02 micron. So they're very, very small. So anyway, there are four. Okay, so before we talk about the resolutions, let's talk about this pixel as well. So both pixel and then imageries, they can be represented using these pixels, or if you want to call it in a long name, that could be picture elements. Okay, so from this terminology picture elements, you can of course detect, for example, in social science, we have studied that the foundation of a society is family. So family is the brick if you consider a society as a house. So just like that, if you consider this is a picture on your right top, then on the bottom left, I mean from the pictorial segment in the bottom left, you will have these small pixels, which are the units of this picture. So the smallest possible region that it can represent, that's the smallest possible region that it can represent, and these are homogeneous. This cell is homogeneous. That means everything that it has, or everything that it has, this pixel has, they are same. There is no difference inside it. They are denoting a same signal or same entity, all right, or the same value. So that's called pixel. So these pixels, they are represented using digital numbers. Okay, and so these are the digital numbers. For example, 170. So this pixel is represented by a digital number of 170. The next one is represented by a number of 238. And so these digital numbers, again, sorry, the range of these digital numbers depend on the bit of this image. So how maybe this image was 8-bit image. Do you remember bit? I think. So if this image was of 8-bit, so we know that 8-bit equal to 2 to the power 8 equal to 256. That means it can range from 0 to 255. Okay, so that's why any value that you see starts from 0 and goes till 255. There is no signal which is more than 255. So that means if you see 0, now you are seeing these very dark images, very dark pixel. Okay, is the darkest one. That means this 0, that means there was no signal. All right, and then if you think of 255, so here you go, 255, these 255 and 255, these pixels, they are the brightest one. So bright that they turn into white color. Okay, so maximum possible brightness is white, we know that. So they turn into white. You see, I'm saying bright, so that means in this image, anything that we see, or the signals are represented by the brightness, right? The characteristics of brightness. So this is called brightness levels or brightness values. Okay, so here is another term, the relative brightness. So these are called brightness values. In short, we call the BV. All right, so BV is the brightness value, and brightness, based on this brightness value, what we get is digital numbers, and then digital numbers depend on the bit of the image. Don't forget that, this is very important. All right, so what sensor does is sensor records the electromagnetic energy that is coming in to the arrays of diodes, and every diode then interpret that intensity of the signal into brightness values. If it receives no energy, then it turns into black. All right, or it stores a number of 0. If it receives if the energy is saturated, I'm not saying it receives the most energy, but I'm saying, remember, I'm saying if the energy is saturated. And what's a saturation? For example, this is a graph. So the energy increases into the sensor. All right. So this is T, time, and that's energy, for example. So energy is increasing, and at some point, the sensor cannot take any more energy, because this is the capacity of the sensor. So this is the capacity of the sensor, that is S, for example. So sensor can take maximum of this amount. So this amount is 100, for example, for sensor, that's 0. And the time is increasing, the energy is increasing as well, and energy is sort of, we can say it's infinite, right? So the energy is increasing over the time, and at some point of time, it gets flattened out. Why? Because it reaches the maximum level that a sensor can detect. Although the energy is coming in, still coming in, all right? I mean, the energy is still coming in. There is still abundance of energy. However, the sensor cannot record anymore, and that point is known as saturation point, all right? So we say saturation. Saturations. We say it's saturation. So that means the at this point the signals were saturated. So that means the maximum amount of energy that the diode or the sensor can detect, it reached that level, and that's why now it's recording the highest possible range of the digital number or the energy. So in this case, it's 255. So it records these numbers, and then when we turn these numbers into a representation, just like GIS, we have in raster we have multiple values, and then what we're doing is we are representing these values in you know, using different colors or different intensity of the same color. So in this case, it uses different intensity of the same color, which is known as brightness values. So brightness values in turn depends on digital number, and vice versa. Digital number also gets represented with the brightness values. Okay, and the digital number, that means the saturation of the sensor depends on the bit that is designed to it. So some sensors, they are designed with 8-bit. That means they can take every energy that they receive, get you know, divided into these 8-bit categories. And that there are also sensors which are designed with 12-bit information. For example, Landsat 8. So Landsat 8 is 12-bit. Okay, so if you have 12-bit, then of course you can detect 2 to the power 12. So find out how much that is. Okay, and then yeah, just like that. So that's pixel. Okay, and the pixel is the smallest unit for any digital image or picture. So pictures, they can also turn into images. How? As I said, you take one, the photograph, they can also be turned into images. How? You take one photograph and then you scan it, then you turn into an image. So resolution. Now we are going to talk about resolution. And the resolution is, there are 4 types of resolution in remote sensing. So the first one is spatial resolution. So spatial resolution deals with the size of the pixels. So if the size of the pixel is 30 meters, excuse me, for example, Landsat, then we could say that the spatial resolution is 30 meters. Okay. Now, the difference between the display resolution that we have in our modern displays, for example, ultra high definition displays, high definition displays, 3K displays, 2K displays, all right? So in these displays, what we do is we have these displays and then we count the number of pixels. For example, 720, 1020, something like that, or 1080, all right? Sorry, so 720 and then 1080. So in these examples, we say that there are 1080 numbers of pixels in horizontally and 720 pixels in vertically, right? So that's how we define the resolution in our displays. So what I said that's how we define the resolution in our displays. But the spatial resolution, when we add the word spatial, the spatial resolution is something different. Now it's talking about what is the size of these individual pixels. Okay, if the individual pixel, for example, in this example, if we had instead of having the 720 pixels, if we had just 7 pixels, and instead of having 1080 pixels in these, if we had just 10 pixels, it would be divided into 10 10 equal segments, right, in horizontally, and vertically it would be divided into 7 pixels. Now if you want to divide it into 720 pixels, of course the size of the pixels will automatically decrease. However, in spatial resolution, we do not talk about how many pixels are located or how many pixels are found in horizontally and or vertically. Okay, instead we say what is the size of the pixel, because there are lots of satellites and lots of sensors, airborne sensors. They are detecting these optical images, and every sensor is designed uniquely, since you cannot define that, all right, so this sensor can detect 1080 pixels in horizontally, and it can detect 720 pixels in vertically, and all satellites detect in the same resolution. You cannot say that, all right? And sometimes the area that they cover also differs, or the extent of the area they cover also differs. Well, how? Because of the distances they have from the orbit and the surface of Earth. So if the distance decreases, then the area decreases. If the distance increases, then the area or the extent of the area is also increases. Okay, so with so much differences, so many variations. So what we say to omit so many variations, we say now that, all right, so how about we only identify the size of the pixels? If we can identify the size of the pixels, then it doesn't really depend how many pixels are in vertically located or how many pixels are located in horizontally, because as long as we know the size of the pixels, now we can say that how fine detail it can preserve or it can depict. So that's why the 30 meters is the 30 meters in x-axis and 30 meters in y-axis, then 5 meters, for example. So this is spot, One example could be Spot. Okay, so Spot is a French satellite. So 5 meters and 5 meters. So in this 30 meters, you see there is one house. So the house is a little bit less than 90 feet in y-axis, 90 feet in x-axis. And the house is L-shaped, right? So and it's covering almost 75% of the area that is inside the extent of this pixel. And if we represent it in our digital image, then you will see that in satellite image, it's the entire area has turned into the house. So if the house is built up area, now this is built up area. Okay, so now this is built up area. Then when we increase our resolution to the 5 meters, so although the value is decreasing, we said the resolution is increasing. Why? Because the details are increasing, just like this. In this, if this one is full HD, then the resolution, that means the details are increasing. So we have now 5 meters. In these 5 meters, now we have 75% of the image is represented as built up area, and the rest is non-house or maybe vegetated area. Okay. However, we are still failing to identify these borders or the setbacks that the house has from its boundaries. And then we increase the resolution again. That means now the resolution is 1 meter. That means 1 pixel. If we have 1 pixel, then it has 1 meter in x-axis and then 1 meter in y-axis. So when we increase the resolution now in our satellite images, we can identify the setbacks of the house. And what is a setback? The setback is the area which you must left out from the boundary when you are building a house. So when people build a house, they leave some area. Okay, they do not build their house along with the wall of the boundary. You have a wall that is identifying the boundary. We do not make that wall as our one of the wall of our house. Okay, we leave some space and then we okay, sorry. The power drop and hence the connection. So let me go back to this. Okay. So as I was saying, so that's the setback. Okay, the area that you leave from your boundary to the wall of your house. So a few more quick example. So Landsat, ETM, so that's 30 meters, and then Atlas, and then QuickBird. And in QuickBird, it's a 1 meter resolution, I think, if I'm not wrong. And in this 1 meter resolution, you can identify these maybe this is stadium or something, a track for running. We can well identify the roads, we can identify the houses, we can identify the trees. Okay, maybe this is a swimming pool or some sort, we can identify that. And this is something else, we can also identify that one. In Atlas, however, we see the patches of vegetation, but we clearly cannot identify their boundaries. We can say, all right, these might be houses, but we cannot say it for sure that whether it's house or not. Same is for here. Okay, we cannot say that we know that this one is a stadium or you know, the running track. We cannot say that, and so on. And if you see in here, the energy is saturated so much, some of them are reaching their maximum level, so they are turning into very, very white. Okay, whereas in QuickBird, it's not that white at all. These areas are quite white because these are the material of the roof is something so reflective that it's almost reflecting the energy that is being incident upon. Sorry. Okay, so similar incidents are going on in both Atlas and then Landsat. However, in QuickBird, in this bottom right corner, we see that the energy is not that much reflecting. Rather, we see a roof which is actually dark. Okay, it's not so much energy is coming being reflected from this surface, whereas in Atlas it's very bright. Okay, so and then we look into this Landsat ETM Plus. So ETM Plus is Enhanced Thematic Mapper Plus. So this is Landsat 7, and if we look into this image, you will be at lost. I mean, where are the vegetations? The boundary of vegetations are not clearly defined because the size of the pixel is 30 meters by 30 meters. So the vegetation has to be, excuse me, they will, excuse me, they have to be 90 feet by 90 feet almost. So there are hardly any vegetation which are almost 90 feet by 90 feet. However, if you have some forest, then you may say that, all right, so this is vegetation because the forest is a large, containing a large area, or maybe you have a grove of different plants. So if this is a grove, for example, in this QuickBird image, you find that there are a collection of trees. They are so making it something like grove, then they are quite visible in these Landsat images. Pixels, they say that, okay, these are vegetation. But then this running track or the stadium is completely lost. Okay, instead, we're seeing only these green pixels. That means you might conclude that, all right, so there are some vegetations, it could be part of forest. Whereas in reality, it's not really a forest, or it's not really these tall vegetations, it's just grass. Okay, in stadium, they have grass, and the grass is reflecting the green light. So now Landsat is seeing these green pixels. So now what we do is we we represent them using false color. So what's a false color? I'll come back to that, not now, later on. So just in short, the true color, there are two types of colors. One is true color in remote sensing, another one is false color. So true color is when you are seeing green as green, blue as blue, and red as red. Okay, in false color, you do not see red as red. Instead, maybe you see blue as red, and then you do not see green as green. So if any channels of these three colors, red, green, blue, get mixed up and represent a different color, okay, or get represented by a different color, that's false color. So in this example, red is represented. So I'll write it down so that you understand more. So red R is getting represented by near infrared. Okay, and then green is getting represented by red, and blue is getting represented by green. So this is the band combination. This is called band combination. So the band combination of this false color is near infrared, red, and green. Okay. So in Landsat images, the near infrared band is number 4 band, so we say 4, 3, 2. Okay, so 4 is near infrared, red is 3, and green is 2. The blue is 1. Okay, so this is false. So if this is Landsat, then we would be saying it's 4, 3, 2 false color, and if the true color would be 3, 2, 1. Why 1? Because 1 is the blue, 2 is the green, 3 is the red. Okay, so RGB, red, green, blue, red, green, blue. Okay, so this is true color combination. Don't worry, you will be getting hang of it over the time. Let me quickly check whether it's getting recorded or not. It is. So now when we use these false color images, then it's quite easier to understand where are the vegetations are, because the vegetations, they have high reflectance in near infrared band. So since near infrared band is put into this red channel, so red is of course having very high reflectance. Since red is having very high reflectance, all the vegetations now they are turning into red, and red is clearly identifiable from other colors, so we can easily identify the vegetations. So 1 meter, for example, again, QuickBird, you see QuickBird, Atlas, and Landsat. So QuickBird, Atlas, and Landsat. So this 1 meter image, all the vegetations are clearly identifiable. Also the roads can be distinguished very clearly, and the shoreline, waters, even the ships. Okay, and the shadows as well. But then when we decrease the resolution, and when you're talking about Atlas, which is 10 meter resolution, now the lakes or the canals or the water bodies, they are not clearly identifiable, and we see these shades or haze in the shoreline. Also, the similar incident is going on with the roads. So the roads are these blocky things, which in reality they are quite smooth lines. Okay, and then when you turn into Landsat, the more details are lost, and now the shoreline is just being represented with straight some line, whereas the pixels are containing multiple values. Same with the streets. So in this street it's just white. Okay, in this street it's a mix of white and a little bit of some other colors, because some of the pixels have some percentage of vegetation. So the signal is changing a little bit. However, when we come to this, then we know that this is a pure pixel. So that means pure pixels mean maybe this pixel, or maybe no, there is no pure pixel. Okay, because the road is very small. It's not 90 feet in width. So this pixel is impervious surface. So this is the house or some bare land. Okay, and the street. This street is almost lost. We do not see it. We see there is a mix of vegetation and some other classes. Okay. However, in this area, we see there are vegetations, and we can find the water bodies, can identify the water bodies because they are covering a large ground. Okay, same is the water bodies. But then now the ships are lost. The ships, they could be identified in this image to some extent, but in Landsat they are completely lost. Instead, they are adding some sort of noise to the pixels of water bodies, because ships, they are made of metals, so of course they reflect different energy than water bodies. So that's why now the water body pixels, most of the areas of these pixels, they are from waters, the signals that I mean the signals. However, some part or some percentage of these pixel is pixels, the signal is coming from these boats, right, or the water vehicles. So that's why these pixels, they have different values, brightness values, or the color values than the surrounding pixels. So in short, the details are lost. Next resolution, that is the number 2, is known as temporal resolution. So from now on, if I ask you, what's the resolution of your image? You must not directly answer me that, okay, sir, the resolution of the image that I'm using is blah, blah, blah. You should first ask me, sir, what resolution do you ask about? Not what resolution are you talking about? Is it spatial resolution, or is it temporal resolution, or is it something else? So at that time, I should tell you that, okay, I'm asking about the temporal resolution. Then you should answer, okay, so the temporal resolution is such. And also, whenever you will be asking someone else, what's the resolution of your image, you should always identify the resolution that you are talking about. You may say that, what's the spatial resolution of your image? Okay. Don't forget this. So temporal resolution is simply, it's very, very straightforward. It's simply the revisit period. Okay. So I think you have studied geostationary satellites and polar orbiting satellites and LEO, MEO, GEO in your what's the name of that course? Early morning, right? Do I need to repeat all these orbits or the orbital satellites? Yes or no? Okay, maybe you guys have forgot, so I will try to talk about these in coming lectures. So revisit period is the time that it takes to come back to the same spot. Okay, so one satellite goes around the Earth. For example, if this is Earth, then one satellite is going over like this. Okay, and then it comes back to one spot, although it doesn't really goes like this way, rather it goes in this form. So it starts from orbit 1, okay, then goes back and comes here again, so that reaches the second orbital path and goes that way and comes back in, okay, and follows the next line. So next orbit is this one, okay, sorry, so let me use a different color. So maybe it's using this, oh, it's purple. Purple would be a good choice, I think. So it following the next line in this manner, and it's going on, and then coming back and coming back and coming back, okay, coming back and so on. It goes like that. So at some point, then what it does is it comes back to the initial orbital path, so which is this, and then it goes like this and comes back where it has started at this point. Okay, so how many days does it need to reach this initial point or reach one geographical point? So for example, Dhaka, we have Dhaka. So Dhaka is located, for example, here. So you have to count how many days does it take to revisit Dhaka again. So Landsat takes approximately 16 days to 17 days to revisit one area. So within these 16 or 17 days, it's actually going to different part of the world. Okay, and then after 17 days, then it's coming back to this region that when it visited 17 days ago. So this revisit period of specific geographic location, which is not written here, okay, so you must write it down. Specific geographic location, revisit period of and specific geographic location is the temporal resolution of satellite images. Okay, so now I would like to ask you, what is the temporal resolution of Bangabandhu satellite? Yes, anyone? Bangabandhu satellite revisit period কেউ জানে না? It's okay if you do not know. I also don't know. Okay, but it's very fast. Although Bangabandhu satellite is not any optical satellite, it's rather a communication satellite. However, if it was a optical satellite, then the revisit period would be very, or the temporal resolution would be very high. So very high means it takes very short time to revisit that area. And why is that? Because Bangabandhu satellite is a geostationary satellite. So that means it's always located on the same spot, covering specific geographic area. So if this is Bangladesh, then it's almost it's actually on top of it's actually located in this region. So if this is Indonesia, then it's located in this region, Bangabandhu satellite. So it's covering a little bit of Middle East and then all these regions, right? So that means it can collect images. Let's say if it can collect images in every 30 minutes, then the temporal resolution of the geostationary satellite would be 30 minutes. If it can collect images in every 30 seconds, so this is minutes. If it can collect images in every 30 seconds, then the temporal resolution is 30 seconds, because in every 30 seconds it's taking images. All right. So what are the another good example of this? So a good example would be Meteosat, or the satellites that you use for weather monitoring, for example, cyclone monitoring. So these are geostationary satellites. They sit on 35,000 or 36,000 kilometers above the ground, covering a very large part of an area, sometimes maybe even one hemisphere of some sort, okay? And they observe continuously what's going on the ground. So that's why whenever you are watching a cyclone or the propagation of cyclone, you will see how these cyclones are moving forward in every 2 minutes, 3 minutes, or 5 minutes, or half an hour, because those satellites are taking photos in every 30 minutes of the same spot or of the same region. So that's why their temporal resolution is very high. Okay, 30 minutes. On the other hand, the polar orbiting satellites, they have some orbital path around the world. So they goes to one pole to another pole, and then comes back to a different region of Earth, and then goes back to a different pole. Okay, so they have some orbital paths, and since they have some orbital paths, they goes over a different region of Earth and eventually comes back to the initial location, or the location that we are area under our investigation. So that's why they need more time than this 30 minutes or 30 seconds. They need days to revisit this period. So Landsat has 16 to 17 days, and then Sentinel has, I think, 5 days. Okay, And why Sentinel has 5 days, so much less than Landsat, although both of them are located in the polar orbiting satellite. Both of them are polar orbiting satellite. That means they are sitting almost 700 kilometers from the ground, up from the ground. Okay, so just remember 36,000 kilometers from the ground. That's geostationary. So it's, if this is polar orbiting, geostationary would be sitting somewhere here, okay, and looking at the Earth. All right, so it's very, very far away. So that's why they cover larger ground. On the other hand, polar orbitings are very close to Earth, so they cover less ground. But since distances are quite shorter than geostationary satellites, the resolution is higher. Okay. On the other hand, geostationary satellites has very low resolution. For example, 1 kilometer per pixel, something like that. So now, so Landsat is just one satellite. Okay. So around Earth, Landsat is a single satellite that is moving around. So one satellite is covering this ground, so it's taking 16 days. On the other hand, what Sentinel has a constellation of 2 satellites. Okay, so those 2 satellites are locating in a different parts of the world. So if this is Earth, if this is the axis of Earth, if this satellite is going down, then this satellite is from the other side, it's coming up. Okay, so now since you have 2 satellites to cover the Earth, but both of them are giving you the same signal, okay, so the revisit period gets divided by 2. So if you have 16 days, it gets divided by 2. Okay, so the 16 days divided by 2 is 8. So theoretically, if you have 2 satellites in Landsat, just like Sentinel-2, your revisit period would be cut down into half, and you would have 8 days of revisit period. That is, the temporal resolution would increase twice. Okay. However, the Sentinel, the satellite, moves a little bit faster than Landsat. So that's why the revisit period cuts down to the 5 days or 7 days. Okay. So the temporal resolution, that's temporal resolution. So yes, there is a relationship between the survey or the images, the frequency that we take, and the ground resolution that we can cover. So the ground resolution is the resolution, is the spatial resolution. We should say spatial resolution, and it's the repetition rate. So that is the temporal resolution. So this is temporal. Temporal resolution, okay, and this is the satellites or the technique that we use. So if we take terrestrial survey, that is, if we use these machines, GPSs and other devices, if we go, then their resolution or the accuracy is very, very high, sometimes 0.000 meters, because you are knowing your location exactly. If you set up a GPS station in your house and you exactly know that where you are and what's on it, you would be standing on your roof and you say that, okay, this is my roof, this is concrete, this is built up area, and then you go under a tree and you take the measurements using the GPS, you find out your coordinates, and you exactly know that at this coordinate very precisely that this is vegetation, this is a tree, this is a vegetation. And even you could record what kind of tree it is. Okay, is it a mango tree, jackfruit tree? Okay, what's its scientific name, and so on. So these things are called terrestrial survey. I mean, there are lots of topographic maps and land cover maps which were mapped out maybe in 20th century or 19th century. Okay, so all these maps, they were done using this terrestrial survey. So, however, this survey, they took very, very long time to repeat. That means the temporal resolution is very low. Okay, and then aerial photographs. So they are quite expensive because you have to fly a plane. Don't get confused with these photographs. Okay, so they should be images. So aerial photograph could be photograph and images, but satellite should be images. But here satellite photograph is for different meaning. So the aerial photographs, they are quite expensive. So the machine is expensive. Flying is expensive. Everything is expensive, and then you also need this collaboration between governments and agencies. So it's even time consuming. So that's why it might take 5 years to take another aerial photograph of the same region by the same agency or by the same research group. Sometimes people do not even take any more aerial photographs or aerial imagery over the same region. Okay, for example, there is a very nice paper of mangrove forest by I think it was Simon and his teams over Western Africa. It has the tallest mangrove trees. So they took this aerial survey. They did the aerial survey using LiDAR data. However, they never went back to this point. So they took this data, I think, back in 5 or 6 years ago, but they are not going to collect another aerial survey in this region. Maybe in future, but not till now. So it's even longer than 5 years. Okay. Then the satellite photographs. So at the very beginning, they used to collect photographs before these digital sensors invented. Okay. So these satellites, they could have taken 3 years to revisit because the satellite is going and then it's taking photo and then it's flying away. Okay. For example, let's say Voyager or that sort of satellite. And then we have Spot. Spot is 26 days. It has a digital sensor. So it comes back every 26 days of the same location. But the resolution decreases to 15 meters. Okay, so per pixel is 15 meters. And then we have Landsat, which is 17 days. And the resolution is 30 meters. We have NOAA. So NOAA sits very, very high on the sky. So it takes every 12 hours one image, and the resolution is 1 kilometer. Okay, so NOAA is by these 12 hours. Now you know that this is a geostationary satellite. Okay, so it's sitting at one spot, looking down, and every 12 hours is taking a photo. Okay, it's taking one image. And the Meteosat, it monitors the weather. So every 30 minutes, it takes one shot. Every 30 minutes, another shot. After 30 minutes, another shot. And the resolution is 5 kilometers. So since 5 kilometers, it can cover large ground. So you see there is a negative correlation between these. Okay, there is a negative correlation between the resolution and the temporal resolution, between spatial resolution and the temporal resolution. All right. Okay. So that's the end of today's class. Before we end today's class, I would like to show you just a quick demonstration of NB Classic. Okay, just quickly, can you raise your hand if you have downloaded and installed the software that I gave you the link? No one yet? Okay, no problem. So this is, I think this one is, so this comes with the software, this data, and I think this is from Landsat because it says thematic mapper. So thematic mapper is Landsat 4. Okay, so 4 and 5. So that's why band 1 is the blue band, band 2, so blue, green, red, near infrared, and so on. All right. So band 1 is the blue, the next one is the green, the next is red, then next is near infrared, then 5 is the middle infrared 1, and 7 is the middle infrared 2. So you may ask, sir, what happened with 6? So 6 is thermal band. Okay, so that's TIR, thermal band. So these are optical bands. So thermal band detects the thermal energy, that is the temperature, that is the heat. Okay, and this one detects the wavelengths that we can see, that is 1 to 3. We can see 1 to 3. Okay, but the rest we do not see, but they're very close to the visible wavelengths. So that's why. Anyway, let me first load out in grayscale. So load band 1. So in this region, band 1 seems like this. Okay, so this is the region. You see, this is how band 1 looks like. So that's blue band. Let me show you band number 2. That's green. So okay, so this is the actual image, and these are the red one that I'm left and right.
Sir. Sorry, pura black দেখা যাচ্ছে।
Oh, তোমরা কি দেখ right. Okay, so আমার slide কি হচ্ছিল? Okay, এবার কি দেখতে পাচ্ছ? And why Fahim is calling me? ফাহিম তোমাদের সাথে না, তোমাদের ব্যাচেই তো। এখন কি তোমরা দেখতে পাচ্ছ?
জি স্যার, এখন
Okay, so let me bring all of the software. Where is it? Yes, and okay, and zoom 4x. Okay, so now if I move okay, so let me open again display 1, new display. Okay, let me close this. So this is NV Classic. All right, so just there is nothing if we close down all these things. So it's just like that. You open one image. Let me close even this one. So I'm going to file, then open image. Then for example, I'm going to select this file and click open. So it tells me that all right, so now you have opened this scan_tmr img, and it has these 6 bands. So band 1, band 2, band 3, band 4, band 5, band 6. And in every band you see these values 0.4850. So that's the wavelength that it was collected, okay, representing the range of 0.3 to 0.4 micrometer or micron. So band 2 is collected at the 0.56 micron, okay, and it's representing the signal of 0.5 to 0.6 micron, okay, which is green. And band 3 is collected at 0.66 micron, so which is red band, and it's representing the range of 0.6 to 0.7 micron. So band 4 is the near infrared, and it is collected at 0.83 micrometer. Band 5, okay, which is middle infrared 1, is collected at 1.65 micron, and band 7 is collected at 2.2 micron. Now you see, as I was saying earlier, the band 6 is missing because it's a thermal band and it does not collect any optical signal. So that's why we left it out from this example. So now let's fire up this first band into grayscale. That means only the brightness values. How does it look like? So load band. Now I have 3 displays. One is the scroll display. Okay, in this is the entire image, and I can sort of move around and see only this part is now displayed in this display. Okay, and then if I move a little bit left, then this whatever in this red region, red square, is getting displayed in this region, in this view. Okay, so this view is the band 1 view. And now in this view again, you have this red box. So this red box is again displayed in this 4x zoom view. Okay, so you can actually zoom in. So you can say, I want to see something more clearly. So you can click here and then zoom in, and you will find out that this box, the size of this box is decreasing. You can also zoom out, all right, to see more, less details, but cover more ground. Excuse me. So that's how it looks like in this region. That's how blue band looks like. Let's see how green looks like. So that's green. Tell you what, let me show you blue first, and then add one new display, and then load in display 2 is, that's the green, and new display, and that's the red. Okay. So now we have blue, and let me put everything in the same spot. So blue, and then we have green, and then we have red, right? So they sort of look like similar, not much difference. So now I'm going to select RGB color. So that's RGB. So this is the red channel, green channel, and blue channel. So automatically it selected the red band as in the red channel. Okay, so this is should be, so green should be, red should be the 3. It's selected. Green is band 2. Okay, and the blue is band 1. So now that's a true color image, and I'm going to select it into a new display, load RGB. So that's how it looks like. Okay, it's something like a mountainous region. This is a valley. All right. So if we zoom into these categories, we see vegetation. Okay, and now I'm going to load a false color image. And what's a false color? The false color is whenever a channel, it get mixed up. I mean, red is in this true color image, red is in red, blue, green is in green, blue is in blue. So if we mix up, let me add a new display. And then if we mix up, if we say in this red channel, I'm going to input band 4, which is near infrared. So you see in red channel, it's saying it's red. It will be represented as red color. Okay, it will be represented, the values of this band 4 will be represented in red color. The values of band 3, the red bands, will be represented in green color because I put them in the green channel. And the values of green would be represented in the blue blue color because I put them in band 2. I put them in the blue channel. Okay, although they are green, but I put them in the blue channel. So load RGB, and that's how they look like. So let me close down these. All right, and we can compare them side by side, true color and false color. Yes.
স্যার আমাদের কি সেন্সরের মধ্যে কোনো প্রবলেম থাকলে ট্রু কালারকে ফলস কালার দেখাইতে পারে নাকি এটা আগে থেকে ইনপুট দিয়ে রাখি?
এটা ইনপুটের ক্ষেত্রে, সেন্সরের ক্ষেত্রে প্রবলেম থাকলে ফলস কালার দেখাবে না because the sensor is always collecting these as for Landsat TM, it's always collecting all these bands সব সময়। হ্যাঁ, সে সব সময় এই 7টা ব্যান্ড সে কালেক্ট করছে ইনক্লুডিং দ্য থার্মাল ব্যান্ড। তো কোনো পিক্সেলে হয়তো সে সিগন্যাল নাও পেতে পারে। ফর এক্সাম্পল Landsat 7 এ যেমন গত লাস্ট ক্লাসে দেখিয়েছিলাম যে এসএলসি এররের কারণে মাল্টিপল লাইন বরাবর সিগন্যাল পাচ্ছে না। ওকে, but it always collects this band information. Now it's up to you, how would you visualize these bands? ওকে, এই যে ডিসপ্লেটা পাচ্ছ, এই ডিসপ্লেটা কিন্তু স্যাটেলাইট আমাকে সরাসরি দিচ্ছে না, সে আমাকে শুধু ব্যান্ড ইনফরমেশন দিয়ে দিচ্ছে। আমি এখন কি করছি, আমি এই ব্যান্ডগুলোকে মিক্স আপ করে এই ডিসপ্লেগুলোকে দেখছি। বুঝতে পারছো? সো ইয়েস, there are ধরো ক্লাউড থেকে শুরু করে so many other things can influence the signal, and that's why we have to pre-process. We have to process the satellite image before we use them. So if you go back to previous lecture, in this remote sensing processes, I have note down what's going on. Okay, you have to do the pre-process before running the process. That means you have to prepare the satellite images before using them. Anyway, just a quick comparison. Look at this. In this true color image on the right, it's in the valley region. It's quite difficult to identify the vegetation because all the settlements and other geological features, they sort of look like vegetation. Green color and gray color, they are quite close, right? However, when I have displayed the image in false color, now these vegetation, they are clearly identifiable. Okay, you see the red dots, these are vegetations, and here are the mix of vegetation and the urban area. Okay, and the vegetation on the mountainous regions, they are also clearly identifiable. So if we go a little bit right, so I've linked these two displays, so that's why it's moving automatically. So if we identify and if we go this region, in this zoom view, it's quite not possible to identify the vegetations. Okay, I mean this pixel, this one looks like vegetation as well. If I zoom in, so see, this area looks like vegetation as well. It looks like green, a little bit green, but in reality it's not vegetation. It could be water bodies. Okay, it could be water bodies because in this region it doesn't say it's vegetation. So now how can you detect water bodies? Let me fire up a very quick grayscale view or even bands TM5 and say new display and load band. Okay, so link displays, yes, okay. So if we go back, where was the কোথায় জানি ছিল? Okay, so right, we were talking about something like this pixel. So this pixel in this image, not really this pixel. Okay, I think I have lost the location of that pixel. Okay, so this one is also a quick good example. This one seems like vegetation. Okay, but then see, this is green, this is also very close to green, and here is very green. So a little bit of urban area in this region. So and then very dark green or dark pixels in this region. So we might conclude that okay, so these are vegetation. But then when we look into this false color image, we see the vegetation are these regions, they are red, but then this one, this area is not red. Okay, so that means it's something else. So which can be close to green. In reality, it might looks very close to green, and that's water bodies sometimes. Okay, because in reality, if you go to a lake, even if you go to Monpura Lake, the water sometimes look a little bit green or dark. Okay, so then what we can do is we can load a band 4 or band 5 or band 7 image, and we can identify the same pixel, and this pixel says that, okay, so these pixels are dark. That means not much of these signals are getting reflected in these from these pixels. So that means, yes, that could be a water body, but the water body is not very deep. It's a shallow water body. Okay, and how do we say that? Because water bodies, they do not reflect at higher wavelengths. They have only a little bit of reflectance in blue, green, a very low in red, and almost zero in near infrared channel. Okay, and then if you increase the wavelengths, they do not have any reflectance. So that's why I have load one higher reflectance band here, and I found out that, okay, so this one doesn't have any reflectance, so that's, of course, that could be water body. To find out the similar thing, we can zoom into these water bodies, and you will see the water body is very dark in these pixels. Okay, they sort of have nothing. So right, yeah, so they sort of have nothing in this image as well. So now they look like blue because they are larger area this river is, and then in this true color image, still the water body is not really identified as water body pixels. Okay, I mean, you cannot distinguish them from the vegetation pixels. However, in false color, they are easily identifiable. So these are water bodies, and these are vegetation, and these are something else. And then high wavelength bands, they are even more clearly visible. All right. So download the software, install it. Does anyone have any question before I close this meeting? No? Very good. Let me close the recording then. Stop the recording.